Let's take a look at the Pythagorean trig identities. Now, they're all based around the unit circle. So let's draw that in. So the radius is 1. We'll make an angle with the x-axis. So again, it's our acute angle there, theta. Now, we know the equation of the circle is x squared plus y squared is equal to 1. And the y value for this triangle, we could work it out. Opposite over hypotenuse, y over 1, so y is sine theta. Similarly, we could work out that x is the cosine of theta. Well, if we substitute that into our equation of a circle, we get the first of our trig identities. Sine squared theta plus cos squared theta will always equal 1. Does not matter what size theta is. Now, to create the next one, we divide everything by sine squared theta. So sine squared on sine squared, well, that'll become 1. Cos squared on sine squared, that'll become cot squared. And 1 on sine squared, well, that's cosec squared. So there's the second of our trig identities. And the third one, instead of dividing by sine squared, we'll divide everything by cos squared. So sine squared on cos squared, tan squared. Cos squared on cos squared, 1. 1 on cos squared, sec squared. So the three Pythagorean trig identities. Sine squared plus cos squared is 1. 1 plus tan squared is sec squared. And 1 plus cot squared is cosec squared. In addition to that, when solving these problems, there's a useful little relationship. Now, it's not a Pythagorean trig identity. It's just an identity of trig. So sine theta on cos theta is the same as tan theta. Let's have a look at this first example there. We're told that cos theta is 3/4, but tan theta is negative. Find the sine of theta. Right, so I'll draw up a triangle. I'm told that cos theta is 3/4. So adjacent over hypotenuse, it must be in the fourth quadrant because tan is negative but cosine is positive. Well, let's work out the third side, bit of Pythagoras, square root of 7. It's in the fourth quadrant, so sine theta will be negative, and reading off my triangle, root 7 on 4. Okay, let's play with the trig identities. Now, 1 minus cos squared, you might see this one straight away. But if you don't, always go back to using one of the trig identities. The nice thing about the trig identities is they all involve different ratios, so we know which one we have to use. So 1 minus cos squared theta. Now, it might look like a silly way of doing it, and let's pretend we don't see it. So I'll substitute in for cos squared. But sine squared plus cos squared is 1. Therefore, cos squared is 1 minus sine squared. And tidying that up, we end up with 1 minus 1 plus sine squared, which is sine squared. So 1 minus cos squared is sine squared. Now, after a while, if you haven't already picked it up, you'll see that straight away. And so you just write it down straight away. You wouldn't do all that working out. You'd have 1 minus cos squared. Oh, that's sine squared. Let's do a similar one, sec squared minus tan squared. Again, you might not see it straight away. I've got a choice. Will I substitute in for the sec squared or the tan squared? Well, my trig identity was 1 plus tan squared is sec squared. So it makes more sense to substitute in the sec squared. So I get 1 plus tan squared minus tan squared, 1. Tan theta cos theta. Ugh. Well, hang on, there is no squareds here to substitute into. So this is where we'll rely on that useful little relationship of tan theta being sine on cos. So whenever in doubt, change everything to sine and coses. So tan theta is sine on cos, times cos, coses cancel, sine theta. Now, we want to prove this particular relationship. 2 sec squared alpha minus 2 over 4 tan alpha is tan alpha on 2. All right, I'm going to start with the left-hand side here. 2 sec squared alpha minus 2 over 4 tan alpha. Well, I see a trig identity there. Sec squared. I know sec squared is 1 plus tan squared. So I get 2 lots of 1 plus tan squared minus 2. Well, tidying the top up, the 2's cancel, and I now have 2 tan squared on 4 tan. Tan alpha on 2. The thing with this is do not leave steps out. The reason for that is it's a proof, and they've told you what the answer is. So you can't just jump straight to the answer. They need to see you working out. Right? So make sure you're working out. Now, if you think you could be accused of fudging the answer, then write an explanation. How did you go from that line to that line? So they can see that, yeah, no, you did actually work it out. You didn't just write down the answer that they gave you. Another note on trig identities, ways you can do it. You can start with the left-hand side and prove the right-hand side. Most people generally try that first. But it is okay to start with the right-hand side and prove the left-hand side. In fact, another way, a third way of doing it, is some people like to work on the left-hand side. They'll do some working out. They might get to a point and they go, oh, geez, I don't know how much further I can go with this. So then they start working on the right-hand side and they end up showing they're the same thing. Well, if they're the same thing, therefore they must be equal. But the one thing you never ever do is you do not solve it like an equation. Like for this particular one, part 3, it would have been incorrect to cross multiply here. It's not an equation. It's something you have to prove. Because we don't know it's true, we can't do it like an equation. We have to prove it's true. Okay. Another way I could have done that, as I say, I could have started with, if I wanted to, the right-hand side. So tan alpha on 2. What am I going to do there? There's not a lot I can do. I could change the tan alpha to sine on cos, but that's not really going to do a lot for me. I haven't got a square, so let's create a square. I'm going to have tan squared on 2 tan alpha. Now, tan squared, I could rewrite as sec squared minus 1. Hang on. If I multiply top and bottom by 2, I get 2 sec squared alpha minus 2 on 4 tan alpha, and that's what I was trying to prove. It gets there, but it's probably just a little bit more fiddly. I don't know that in reality I would do it that way. Here's a fourth way you could do it. Some people like to move everything to the left-hand side and just show that that's equal to 0. So now, instead of proving what they want, I'm going to try and prove 2 sec squared alpha minus 2 on 4 tan alpha minus tan alpha on 2 is equal to 0. Note, this is not solving like an equation because I'm just rearranging what it is I'm trying to prove. Once I start my proof, again, it's not an equation. You see, because you start your proof, there's no equal sign there. It's an algebraic expression. So this time I'm starting with 2 sec squared alpha minus 2 on 4 tan alpha minus tan alpha on 2. All right, common denominator, let's make it 4 tan alpha. On the top we get 2 sec squared alpha minus 2 minus 2 tan squared alpha. The sec squared I can change to 1 plus tan squared. And look what happens to the top. We've got 2 plus 2 tan squared alpha minus 2 tan squared alpha. Well, all of that is 0. Well, now that I know that that is true, now I can treat it like an equation. So now I move the tan alpha on 2 to the right-hand side, and there's my proof. 2 sec squared alpha minus 2 on 4 tan alpha is indeed tan alpha on 2. Okay, so 6F and 6G playing around with these trig identities.